Alright, today we're going to work on the backward pass of the Lora layer. We are going to do two different versions. This is actually my second time recording it because I messed up the first time. So, a bunch of the code's already written. And we're just going to go through that, and because I don't feel like rewriting all that. That's a lot. Talking is exhausting. So, yeah, we're doing the backward. We're going to do two different versions. There's the efficient one, and then the one that uses a lot of memory creation and access. This one will help a lot with the intuition of stuff, and then the regular backward will be a much more efficient one, obviously. I think if we just went straight into the efficient version, it would be very unintuitive and very hard to follow. So we're going to start with this one, and then we'll do this one. Let's see here. So this should all be here from the last video. Before I actually get into the code, got a visualization here, and the visualizations were actually messed up. But okay, so we got a regular dense layer right here. Going forward, we have the inputs, we have the weights, and then we have the outputs. XW equals O output. And then when you go backwards, you have the same shape as the output would be the derivative values from the forward layers. Those forward layers, in order to get the gradient of the weights, we do forward layer times the inputs. I am right now ignoring matching of dimensions and also ignoring which one goes which. The left and right hand side matrix stuff. All I'm saying is derivative values flowing back in order to get the derivatives of these weights. These forward derivatives multiply with the inputs. If you remember right here. Derivative of the weights, those d values, the forward, future layers, forward layers, derivative value combination multiplies with the layer inputs to get the weights. And then the same thing here for the derivative of the inputs. You do the weights times those derivative values. And that's going to help me explain how you do the back prop for Lora. So Lora, we have the inputs, we have the A matrix, A weight matrix, and the B weight matrix. And then the output. Going backwards, you would have derivative values, which are the same shape as the output. And so let's say we wanted to get the derivatives of the A weight matrix. What you do is you pretend, okay, so you pretend you have inputs times the A weight matrix, and that'll get you its own output, which is after here. So this times this equals something. It's not going to equal this exactly, because that's just something else you combine on to get here. So it's not going to equal this, but this times this does equal something here, which means if you treat this as the weights, what we need to do to get the derivative of it would be take the output here, or not the output, the derivative values flowing back past this point times the inputs. in order to get the derivative of these weights. And also to get the derivative of these, I'll just leave that. Derivative of the B weight matrix, what you're going to need is the derivative values flowing back from the forward layers multiplied with the input of the B weight matrix. Well, what's the input of the B weight matrix? It is what we output from multiplying this times this. So this times this gets you a certain weight matrix, and that weight matrix will be the input here that you multiply with the B weight matrix to get the output. So in order to get the derivatives of these two guys, for this guy, you'd take the derivative values here, which we would say flowing back from down here up into here. Sorry, I'm inverting up and down with, or I'm switching from backward and forward to up and down, just because it's easier to make these matrices. So we have derivative values times the B weight matrix would become your derivative values, like your kind of total derivative values that need to multiply with this input matrix to get the derivative of the weight matrix. Hopefully that makes sense. And then you do, in order to get the input of this B weight matrix, to get the derivatives, you need the input. The input is what happens when you multiply these times, and then to get the gradient here, you need that multiplied stuff times your derivative values. Okay, so that's a little visualization. Hopefully it helps to understand what's going on here. First, we're going to put some values here. We'll need the rows of the layer inputs, as well as the layer inputs columns. I'm just putting them in variables. The output columns right there. And then it looks like I proceeded to ignore that completely. Is that what I did? Yeah, kind of. Cool. So that could be helpful, or I don't think we actually need them because I ended up ignoring that completely. Whatever. Okay, so first off will be the layer, the biases, the bias vector, the biases for the layer. This is completely the same as the dense layer. So really, I just copied this whole spot from up here in the dense layer. The dense layer backward. Literally just took this if layer bias, calculate the biases. Took that, copied, and pasted it down here. And then after that, we're going to make transposes for the WA and WB, as well as transpose of the layer inputs as well, because we're going to need those for all those mixed in things of multiplying everything with everything. Makes it easier. And then we have these two values, dval WB and input WA. Input WA is what we get when we're going to combine this with this. matrix multiplying those two, we'll get input WA, and then the deval WB, combination of D values with the B weight matrix. So remember to get the derivatives of A, okay, whatever. We will need its A's, the derivative values that are past A, that are more forward in the layers than A, and that would be multiplying these two, multiplying the derivative values and the B weight matrix gets you a derivative value here, which you multiply with the inputs to get the gradients here. Okay. Yeah, so that's dval WB is a combination of these two. Feel free to, once I go through this, feel free to put in a bunch of print statements to show yourself what's going on, how things are outputting, what shapes, to get a feel for all these matrices. And that's what I use to help visualize this stuff for myself going through it. So if you need that, feel free. So we made this dval WB. We are also going to make the inputs and WA combined, which will be transpose WAT WA. We got to transpose things to match up dimensions. Like I said, do print statements. It'll help you visualize. Do print statements with like the OR. What do we have? The OR statement thing. The OR function, I guess, that we approximated with the neural net. Yeah, you can do. Trying to remember if that's how I did it. Yeah, that would have been how I did it. That is good to do. We are going to skip that. So that's something I'm gonna have you do on your own to figure out stuff for sure. If anyone needs me to go further in depth on that, and showing matrices better and all that stuff, let me know. But I'm just gonna throw this directly into the image neural net here and replace that. Okay, so we're gonna transpose, sorry, get off topic. We're gonna transpose WA here, and then we are going to get, no, I lost where I was at. Okay. I'm just kidding. Don't need that yet. Sorry about that. Do not need that as of yet. Right. Inputs in W. Okay, yeah, I was looking at the wrong line. Okay, so just to do this, we are going to, the output of MP inputs in WA is just going to be layer inputs in WA. layer inputs WA. Remember, this one's going forward, so you don't need any transpose here, because it's just like going through the forward pass. Inputs times WA, just going forward. It's when we go backwards with stuff that you need transposes. My bad. And then we're gonna get DWB, the derivatives of the B weight matrix, with let's see, calculate DWB, derivative of the B weight matrix. And we're going to do that by first transposing, because this will include a going backwards. INPWA, we're going to get a transpose of that. And I believe, yeah, it's always the first things that get transposed. So when we had flow back on the regular dense layer, it's the derivative values with the transpose of the inputs. Well, here we've done the inputs with WA, imp WA, and that's going to combine with the derivative values. So derivative values, pretend this is the input to WB. Well, this needs transposed. So imp WA, we want transposed. And then to get DWB, we're going to do that imp WA transpose and the D values. So that gets us the derivatives of the B weight matrix. And then, let's see, we're going to calculate DWA. So we got to transpose the layer inputs. And then DWA will be equal to layer inputs transposed with dval WB. So that, sorry if I'm over explaining on these visuals, just for if anyone needs it, it's helpful. So DWA will be the layer inputs, but we got to transpose because we're going backwards. And then dval WB, which is the combination of the B weights with the derivative values. That gets us, that is the derivative of all the weights, so that's awesome. And then the last piece we need is to get the derivative of the inputs. Derivative of the inputs. So derivative of these guys. If you go back to our regular dense, derivative of these guys was this times this. So pretending these are the D values times the weights gets you the derivative of the inputs. The weights would have been transposed because they are the left hand part. Well, they end up going to the right hand doing this, but yeah. Yeah, weights transposed with D values gets you the D inputs. And these D inputs are dval WB with WAT, the A weights transposed. Okay, so that's the intuitive way of doing it. That's all. That's where I'll go with this video. In the next video, I will go through the efficient version. I'm just gonna remind myself exactly how it goes, and then I'll make the video.